this, one can also show using the second inequality and replacing what do you call u of s by uk minus u naught of s. Okay, so we can show actually that, and using these two convergences in appropriate sense is important. One can show that 0 to t, the gradient of u minus uk and its square, okay, in h norm b tau goes to 0 as k goes to infinity. Okay, as k goes to infinity. So, what are the conclusions? I want to show this. First, you gotta show these two things. Second, using these estimates, okay, the estimates, the energy estimates, and replacing u by uk and the gradient of and the second inequality, again you're replacing u by u minus uk, and using these two convergences, what we can show is that these both guys goes to 0. So it's not difficult. So these are the small things that you have to work out for yourself. And what actually I would like to show, this diagram. So this is the key thing that I would like to show. Alright. What is the next thing? So I know I'm leaving a lot of gaps for you to fill in. These are what you need to fill. But, you know, you need to also concentrate on the way and the method basically that we are using, you know, to study the, you know, the long-term behavior of this evolution equation in particular. Now, if these two guys are true actually, in other words, if uk minus u converges to uk in h norm and the gradient of uk minus u minus uk is square in h norm also goes to 0, then what we can deduce actually using the Gagliardo-Nirenberg inequality. Which version of Gagliardo-Nirenberg inequality? This version of Gagliardo-Nirenberg inequality. What was it? So here is this version of, let's use this version of Gagliardo-Nirenberg inequality. ULP can be estimated by the gradient of u power p minus 2 upon p in L2 norm, h norm times u raised to 2 over p in h norm. Okay, so using these two inequalities, if in this inequality, if I say replace, what do you call, u by say u of t minus uk of t in LP norms, on this side I'm going to get the gradient of u, p minus 2 over p in h norm and constant, and u power 2 over p in h norm times constant. And if on this, so not u, but you're going to get u minus uk, and here you also going to get u minus uk. And now take on this inequality a power q, that q is 2p 2p over p minus 2. Okay? 2p over p minus 2. When you will see in a moment that why I am choosing this particular norm actually. So if I take u of t minus uk of t raised to say this q less than or equal to c times of this guy will become the gradient of u of t minus uk of t in h norm. So p minus 2 by p multiplied by the power 2p over p minus 2. So this is going to remain with this square. So you're going to get square as a result times times what? Times 2 over p multiplied by p minus 2. So this will become u of t minus uk of t in h norm raised to 4 over p minus 2. You're going to get 4 over p minus 2. So this is what that you're going to get. And now integrate this guy from 0 to infinity, both sides. 0 to infinity dt. Okay? I can take this as supremum and I can pull this out. So I can say that, okay, this is less than or equal to the supremum, where the t is between 0 to infinity, u of t, uk of t in h norm 4 over p minus 2 times 0 to t, 0 to infinity, gradient of u minus uk, what do you call it, square h norm dt. And now take k goes to infinity. Take k goes to infinity. So as here k goes to infinity, u minus uk goes to 0. And as k goes to infinity, 0 to t, gradient of uk minus uk square dt goes to 0. So this goes to 0 and this goes to 0. So the product of these two goes to 0. And once you have this, you can say, so what you can say? Once you have this, you can say, you can put this in combination that uk converges to u in LQ over the interval 0 to infinity with values in LP. So this is what in LP norm. So this is what precisely I have shown actually, that okay, this goes to 0 using these two convergences actually. Okay. Now, what we know about UK and U, so we know about UK and its LP norm and U and its LP norm. So the UK is the solution to the approximate, it's an approximate solution to the Navier-Stokes equation, while this is the global solution of the Navier-Stokes equation. Both are global. In LP norm, they both are uniformly bounded. Uniformly bounded. This is uniformly bounded, this is also uniform. So this was shown in the beginning. This was, we seen in when we were proving the double star actually. So the both are uniformly bounded. And once they are uniformly bounded, then for any p positive and a q prime between 1 to infinity, where the q prime is conjugate to q. Okay. Q prime is any number between 1 to infinity. If I take, say, absolute of UK of T LP norm minus UK of U of LP norm, okay, then by reverse triangle inequality I can say that we're going to have UK minus U in LP norm, okay. So if I raise this to Q, this would be raised to Q or Q prime, okay, and then I integrate it, say from 0 to infinity, and I integrate it, say, from 0 to T, and I integrate this as well from 0 to T. So what does this would show? What does this would show? That you can show actually that this goes to 0 as k goes to infinity. So you can say that UK converges to U LP in LQ prime over the interval 0 to T, okay, for any T positive. This is kind of a strong convergence actually, and once you have this strong convergence, you can get what you call the almost sure convergence, and almost sure, but almost everywhere convergence. And once you have this almost everywhere convergence, now what you can do is that you can take your inequality in YK. So if this is the case, you can also show that your Yk of T, which was UK of T with LP norm and raised to alpha, this converges to Y of T almost everywhere, because the strong convergence implies almost everywhere convergence, to the Y of T U of T raised to alpha and in LP. Okay, this is what that you're going to get for alpha we specified it previously. And now once you have it, so using inequality that we showed that okay, Yk of T minus Yk of S can be estimated by, say, from S to T, okay, and Yk of, say, tau raised to k of tau over P plus 2 over P plus Yk plus Fk alpha LP and d tau, and in both sides you take k goes to infinity. So once you take k goes to infinity, so this will become Y of T almost everywhere, Y of T minus Y of S less than or equal to 0 to T. This will become Y of tau power P plus 2 over P plus Y plus, what do you call, norm of F LP raised to alpha and what do you call dt. So you're going to get this, and once you have this, so you proved, so we have our star condition. And once you have your star condition, then by the lemma, what was the star condition? This is your star and double star condition. You kind of showed that both of these satisfy what you call your required equations actually. Okay. But, both of these are satisfied for this y, and since both of these are satisfied, so by this lemma, we can deduce that y of t goes to 0 as t goes to infinity. And this is really the conclusion of today's discussion. Thank you.